we talked about NMCs or an oxide, the representative of oxide materials coated with another oxide. So now we're going to talk about, in general, how does one approach the selection of cathode coating to design and engineer these interfaces that are beneficial? What are the things that we have to think about when it comes to material selection?
Something that will allow the ions to diffuse through.
Okay, so you want to think about ionic conductivity. Okay.
You don't want to be too electrically resistive.
So you want it to be electronically conductive, but not too much.
Yeah, so want to decrease it too much.
Okay. We'll call that the Goldilocks, somewhere in between, right? Sure. Sorry.
Cost.
That's fair. How you're going to what? Okay, so fabrication, which goes back to the argument or the consideration of oxides. You have to apply higher pressure, higher temperature. Sulfides typically less, lower temperatures. Maybe you can get away with cold pressing. Okay.
Particle contact, so like how well the particles like mess with each other or just like interact with each other.
Okay, so more like particle size,
Yeah.
or okay. Yeah. So maybe morphology, which goes to fabrication, right? Are you going to wet mix, ball mill, dry ball mill, wet ball mill, pulse layer deposition? So it goes back to, are you going to make thin films of these things? Are you going to do atomic layer deposition to get better contact at the beginning? All great considerations. I'm standing here because there's a key word that we're all buzzing around.
Electrochemical.
Electrochemical stability is the name of the game for everything in this class. Yes, this is what we often forget, myself included, because we have been talking and focusing on the intrinsic properties of like the origins of superionic conductivity as it relates to crystal structure, right? The atomic origins of interfacial stability, chemical reactions, right? But at the end of the day, well, where we left off last time, right? If there is misalignment of the chemical potentials from your LUMO and your HOMO with the chemical potential of the cathode and the anode, there is definitely going to be SEI and CEI, and there's definitely going to be chemical degradation. Okay, that's a big one. There is one more in terms of intrinsic, a key. I mean, they're there are many things one can consider, but another intrinsic property of a material.
Crystal? Not that.
So crystal structure, yes. I will lump that in with the ionic conductivity as it has like the atomic origins of that. That would matter if more, that matters, but that would matter more if you have, if you're trying to grow certain surfaces exactly on another surface. I'll include that, why not?
What about, you want it to be, you don't want it to interact with the electron ions, so maybe like a high reduction potential?
Okay, so that goes back, I would lump that in with chemical stability.
Oh, yes, of course.
Yeah. Yes, but that is a, you know, a subtopic within that. Yes, oxidative stability goes along with reductive ability, which is chemical stability. So yes, band gap has everything to do with decomposition, so higher band gap, the better, yes. Think of pressure.
Density. Not that.
Close, you're getting there.
Closely,
Sorry, what?
no. I said closely packed,
Thermodynamic stability.
Thermodynamic stability ties back in with electrochemical stability because your chemical potential is a thermodynamic parameter. So, synonyms.
Would you want it, I don't know if this is the right word, would you want it to be like relatively flexible in case there's some sort of a volume change?
Ding, 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 ding. All right, you get the daily double. Yes, mechanical stability,
Oh, yes.
mechanical properties. Stability is assumed, as in it's not, your material is not going to fracture. If one has to rank, what are the big ticket items that you should be concerned about when you're trying to screen for materials? These are the properties. Because if your material is not as stiff, so if the elastic modulus is not as high, there's potential that it won't be able to suppress lithium filament growth, right? The lithium is going to grow and push your material straight out, right? Grow past. Electrical stability, right? The induction of SEI and CEI, chemical stability, oxidative, reductive potentials. And of course, if your ions are not moving, they're not moving, right? If it's not ionically conductive, then lithium migration has a higher energy barrier, and it's just, you know, well, the activity, the activation energy and also the ionic conductivity, if they're low, if the activation energy is high and ionic conductivity is low, then obviously that's also not a great starter. So these are the properties that you can screen by, because we can map out all of these through DFT calculations. Well, at zero we can understand the trends, right? We can measure mechanical properties and screen all these materials and tabulate them. So that's what we're going to do, right? So phase stability, I didn't mention that because I sort of lumped it in with chemical stability, but in terms of trying to understand, you know, what compounds can form, here's just an example of a bimetallic system, but you also want to understand, okay, if I put two materials together, what is going to be the likely decomposition products? The answer is whatever is thermodynamically favorable, right? So if you have niobium at the interface with oxygen, what's going to form? Niobia, right? But which niobia, right? Is it going to be NBO2? Is it going to be NB205? And are those species going to be ionically permeable? Are they going to let lithium ions to go through? We can predict all of that because we know, as Ezra said, the crystal structure. So that there are atomic origins to all of this, and they're all intermixed with each other. So we can, from density and functional theory, predict, okay, if we have two species for a simple case, or even a more complex ternary phase diagram, we can map out the species that are most likely going to form when we put two elements together, or three elements together, or pseudo-binary. You know, you have two binary end members. What does that form? So we can make what's called a convex hull. So you can run DFT calculations and say, okay, at certain compositions and mixing, what is the energetically stable phase? So that's the lowest point. Okay. I should do it on here, sorry. What's the lowest point on this energy curve? So the formation energy of the singular of just the element is going to be 0 by definition, right? Elements, single atoms don't form themselves, so it's the definition is 0. Anything below that, these negative, the lower values, the better, the more energetically favorable. And so then you can say, okay, well, at these compositions, these are the thermodynamic equilibrium compositions. These are the compositions that are going to form, and anything above that is going to be above the hull, like a hull of a ship. You know? So anything above that is that same composition, but different phases, different morphologies, so they're higher in energy. Now, what's going to be stable? That depends on what your cutoff is. Some structures are stable a few EV above the hull. Some of it, well, half of an EV, a tenth of an EV. You know, there can be different cutoffs for different systems, but obviously the higher ones are most likely not going to be stable. Those phases are not going to form, but the ones that are close to the hull, they can form besides just the most stable phase, which is the lowest energy. So you can just look at formation energy. Now, when we look at phase stability, we can measure the total energy of the compound minus the elemental species. Now, the summation of the chemical potentials, which is basically the total energy of each of the elements. And we can say, okay, well, how stable is this formation energy? And that difference between the compound and what's at the convex hull, the energy of the convex hull, that will tell you the phase stability. The higher the number, the less, the higher off of the convex hull, the less stable. So we can predict all of this, and there are programs out there that try to predict for like thousands and thousands of compounds. Okay, some of them of interest to battery materials. In terms of chemical compatibility, we now make sort of like a pseudo-binary system where you have, let's say, if you want to put a solid electrolyte, some aguridide with NCA, or lithium niobate versus this aguridide, then you can look at the formation energy again, and the top equation just shows you, it's just a linear combination, as in you take the energy, what's the fraction of A, let's say this is A, let's say this is B component, okay, and you just mix it. So that's what those are fractional. How much of A do you have? You mix it with how much of B do you have? And you can just see, what is going to be more reactive. So here in this case, the formation energy, the higher the larger the value, the more negative, it's actually going to be the more reactive of the two combinations. Okay, so we can also try to predict chemical stability when it comes to these different combinations to try to screen our material selection. And then we get to electrochemical stability. So if you look at this this plot here, if you had your choice, which coating material would you pick if you had, NMC as your cathode versus lithium metal? Yeah, you would pick lithium fluoride in terms of electrochemical stability, but is it ionically conductive? That is the issue, right? So this is one component. So then you could think, well, why wouldn't I just make a composite? Why wouldn't I just start blending materials together to basically try to cover the entire range? Now, the other thing you have to consider is, even though these are the calculated stability windows, it's not always that is the only range that they work in. So the intrigue of the SEI and the CEI is that batteries run despite the limited electrochemical stability windows of some of these compounds, right? I mean, we've seen agiridites, all solid batteries with solid state, with a giridite solid electrolyte, and they run, I mean, there's fade, right? But the fact that they cycle at all, right, is an indication that the passivating layer of the SEI and CEI work, okay? So, and then there's the ionic conductivity, and you can see in terms of selecting the families, the compounds, the antiperovskite that we talked about, the giridites, the garnet, the lisicon, thiolisicon, LGPS, and all of that, you can try to pick, the higher ionic conductivity from all these family of compounds to try to achieve that. And then there's mechanical stability, because what we've seen in terms of filament growth prevention or suppression is that for the oxides, what you see are, LLTO, LATP, I've listed some of the more common ones, lipon, the elastic modulus, so how stiff it is extremely high. So these are going to be compatible for lithium suppression, lithium filament growth suppression, because you really just need, for the shear modulus, you just need that, your solid electrolyte to be about twice that of polycrystalline lithium, which comes in at about 4 to 8 gigapascal. So no doubt, your oxides are going to prevent that. But whether or not you can fabricate it so that you can maintain volume, contact and prevent delamination is a whole nother issue. Now, what we haven't talked about are plasticity and also fracture toughness, right? These are oxides. If we know that oxides are stiff, what does that say about their plasticity and also ductility? Yeah, everyone in the audience is like, oh, no, I would never make an oxide for plastic that can withstand plastic deformation, right? Exactly. It's extremely difficult. So there are ways, though, right? You can substitute your oxide with, say, the example I have up there, aluminum, tantalum. Oh, sorry, I'm 2 minutes over. Aluminum, tantalum, and you can, modulate some of the mechanical properties. But that's something that you have to take into consideration, is that the oxides are extremely stiff, and the sulfides are not. When you work with sulfide-based solid electrolytes, the shear modulus comes down to like 7 gigapascal. So it's just not as stiff, and that's actually great, because that will actually help to contain cracks as they form. Okay? Because they now can get into the have better contact with the crack. But higher fracture toughness as well to resist the fracturing and also contain the cracks once they form, so that you don't have basically catastrophic fracture. Okay. All right, so here's a good place to stop before we start next time and talk about space charge layer, as well as all sulfide-based cells. Okay, thanks everyone.